Okay, so in this video, I'm going to comment about section 3.8, and that is implicit differentiation. What is implicit differentiation? Okay, well, implicit differentiation is the process of computing the derivative of an implicit function. Then you want to ask, okay, what is an implicit function? Okay, an implicit function is a function in which we have a mathematical expression in which one of the variables, that is the dependent variable, is involved in the expression and is not really easy to solve for the dependent variable. That's basically the definition of the implicit function. That's what I mentioned over here. An implicit function is a function that can be expressed in this way, equals to 0. Then it cannot be easily solved the dependent variable. So it's an expression that is function of the independent variable, that is x, and the dependent variable, that is y. So y is a function of x. But in this expression, everything is mixed, and it is not straightforward to isolate from the expression the dependent variable, or in other words, to solve for the dependent variable. Okay? So, what is the procedure? Well, before talk about the procedure, let me show you this example. So, this expression that you see here, okay, is an implicit function. But the problem with this implicit function is that if you want to isolate or to solve for the dependent variable y, it's going to be, from the mathematical point of view, very challenging, or probably almost impossible to do it. Okay? So, to reorder this or simplify this, that at the end, you're going to get an expression y equals to an expression that is only a function of x. That is going to be difficult. Okay? So, this is what is called an implicit function. Another implicit function is a circle. So, let me write down here. So, the unit circle, for instance, x squared plus y squared equals to 1. That is the unit circle. That represents, in our Cartesian plane, a unit circle in which the radio, the radio is equal to 1. Okay, but in this case, it's a little bit easier. Even though if this is an implicit function, you can isolate the variable y, because the variable y in here is going to be 1 minus s squared raised to 1 over 2, and this is going to be plus and minus. So it's not really that bad. So we can still doing something. But in expressions like this, it's kind of difficult to solve for the variable y. Okay? So what we can do to compute derivatives in those cases? Well, I found this in the browser, okay, in Google. I Googling just to see if I can find a workflow that looks very didactic and easy for you guys instead of the one that we have in the textbook. And I found this one that is very, from my perspective, of course, looks very easy. And look at what they say. Well, they say, step 1, differentiate every term on both sides with respect of the independent variable. So, in other words, if you have an expression like this, okay, take the derivative respect to the independent variable, that in this case is going to be s, to the both sides of the expression. Okay? Whenever you find y, well, you're going to write down the derivative of y respect to x, which is this one. And then at the end, solve for the derivative of y respect dx. What you're going to do, like a very simple linear equation, you are going to group like terms, and one of the terms is going to be the derivative of y respect to the independent variable x. And you solve for that one. That's it. Okay? That's the way to go with implicit differentiation. Okay? And just to illustrate how we can do that, I made the detail for this exercise. In this exercise, they say, compute the slope of the curve, the black curve here, at the point 4.4 and 4. And they are giving to you the slope, which is 1/5. 1/5 is the slope of this tangent line to the black curve at the point 4, 4. I mean, at this point in which the x-coordinate is 4 and the y-coordinate is 4. In other words, if you substitute here in this expression 4 and 4, this is going to be a identity. I mean, that point belongs to this curve, and this is going to be true. But okay, so what we are going to do? We are going to show that really the derivative of this implicit function respect to the variable x evaluated in 4 is going to be equals, evaluated in the point 4 and 4 is going to be equals to 1/5. Okay, that's what we're going to do to show that. Or in other words, to find the slope of the tangent curve to the black function at that point. Okay, so how we can apply the implicit differentiation workflow that I present over here. Okay, you're gonna see that at some moment we are going to need the application of the chain rule. Okay, so we have the mathematical expression that in this case is an equation, is this one. Well, the step 1, what they say is, well, take the derivative to both sides of the equality sign respect to the independent variable, in this case is x. Take the derivative of that. So this is the derivative of all of this, and because we have here a constant, I can bring out of the derivative sign the constant, and then we have the derivative respect to x of this function equals to the derivative of y respect to the variable x. Whenever we find y, we write down the derivative of y respect to the variable x. That's what they say here in step number 2. Oh, but in here, I have the composite of two functions. The external function is the evaluation of this power, okay, to 1/3. Or in other words, the radical symbol, that is this one. Okay, that is the external function. The third order root, or the power in which the exponent is a rational number 1/3. Either one that you want to identify is going to be the same. Okay, so it's the derivative of this external function evaluated in an internal function. What is the internal function? X plus y. Okay, so what is the derivative of a power? Well, we bring down the exponent 1/3, and then we have 1/3 minus 1, okay? 1/3 minus 1, y. You got it? Okay. Times the derivative of the internal function. What is the internal function? X plus y. So the derivative respect to the independent variable of the internal function or the inner function, that is x plus y, equals of what I compute before. I'm not going to do anything here. So in this step, I apply the chain rule. Okay, in this step over here. Okay, that was the one that we developed and detailed in the previous video. Okay, so what is this? What is this now? Well, this is 2/3, and what I write down was 1/3 minus 1 is 2/3. That in a radical notation is 1 over the third order root of x plus 1 squared. Okay, so what I'm doing is this one. So the third order of x plus y, everything squared, well, this is equal to x plus y raised to this rational number, to 3rd. This is what I'm doing from here to here, okay? This. Identify that this and this are exactly the same. Okay? Then, the derivative respect to the independent variable of this addition. Well, that is the derivative of each one of the member of the addition. So that is the derivative of s respect to the variable s, and the derivative of y respect to the variable y. Okay? Perfect. So let's move over here. So what I'm applying here, the derivative of the addition of two functions. Okay, so this is this one here, this is this, and this is this. Now, I have this expression. Now, I'm going to evaluate the expression in the point of interest, because I want to compute the slope of this pink line, which is the tangent line to the implicit function at this point 4 and 4. So I need to evaluate this function in this point. So this is going to be 2/3 1 over the third order root, and I put it here a square. Okay, I put it here a square because x is equal to 4, y is equal to 4, and let me add here 4 plus 4 is 8. That's what I have here. So we have here a square. A square. Now I bring all these radical expression and saying that is equals to 1/4. Okay, let me just write down over here. So the third order root of a squared is equal to what? Well, look at here. This is the third order root of a squared. But what is a? A is 2 to the third power, everything rise to the second power. Then this is the third order root of 2. What is power to a power? Well, I keep the base and I multiply the exponents, which is 6. And what is this? This is 2 raised to 6 over 3. And that is 6 over 3, which is 2. 2 raised to the second power is 4. And that's what I have over here. So this is 1 over this result, that is 4. Okay? Then I have 2/3 times 1/4. 2/3 times 1/4 is, I can simplify this 2, and then I'm going to have here 2. Then I multiply this 2 denominator, that is 1/6. Then multiply 1 plus the derivative of y respect to the variable x equal to the derivative of y respect to the variable x. So I have this expression. What I'm going to do? Well, I'm going to solve that as a linear equation. I'm going to solve for, and let me write down here, for the y, the x. This is one of the like terms. I'm going to bring all together, and then I'm going to solve that. When I make that, I'm going to get that the y over the x, I'm sorry, the derivative of the function y respect to the variable x is going to be equals to 1 over 5. Okay, that was the exercise. So, in summary, what we have done here, well, we apply the workflow for the implicit differentiation, and in the middle, we apply the chain rule. Okay, perfect. Well, that is the implicit differentiation. Thank you.